Hello everyone. So, first of all, I want to thank the organizers and especially Christina to make this wonderful event happen. And I want to also thank to giving me the opportunity to speak here today. And secondly, the quantum kinetic equations for mixing neutrinos have been studied during the last decades by using many different formalisms and by many different people, including Christina, Georgi, and Gunther, for example. So then, as we have heard during the last couple of weeks, and as we know, neutrinos have many fascinating and interesting properties. For example, the flavor mixing with the possible resonance conditions in hot and dense environments, that is the fast wave conversion. And then there also occurs the particle-antiparticle and helix-to-coherence. And maybe exactly due to this richness of the different phenomena, there also exist many different ways to model the neutrino evolution. And this include, for example, wave packets, density matrices, mean field equations, and so on. However, regardless of the numerous and comprehensive studies of neutrinos, there still exist interesting questions regarding the different coherence effects. And here we will be discussing especially the particle-antiparticle coherences. And at the ultra-relativistic limit, while concentrating to the forward scattering terms, these topics have been studied pretty widely, for example, again by Christina, and the understanding has been that they should not have significant contribution to the flavor oscillation or the flavor evolution of neutrinos. However, when it comes to the collision terms, it is not so well understood if the particle-antiparticle coherence could affect to the neutrino evolution through collisions, especially in hot and dense environments, and if there could occur instabilities or something else which could amplify the effect. And this is one issue that should be studied more. And also there is the question about heavy neutrinos. And there has been discussions by, just forgot the name, but there have been discussions that especially in reactor experiments, if there is like heavy neutrinos, it might be necessary to resolve the particle-antiparticle coherence in order to interpret the results correctly. And this would mean that the existing formalisms should be generalized out of the ultra-relativistic limit. And in addition to that, there exist many different interesting properties, such as decoherence effects, quantum entanglement, how external magnetic fields affect to the possible coherence effects, and many others that I don't have time to mention. And in order to study these, you need some kind of quantum kinetic equations and formalism related to that. And so that is exactly what we did. So, and forgot to mention that this speech is based on 2 papers which are done in collaboration with Kimmo Kainulainen, and to lack of time, I'm not going to give an overview about the quantum kinetic equations, but just concentrating on this one model. So what we wanted to do is that we started from a really fundamental quantum field theoretical standing point, and we indeed derived a set of quantum kinetic equations which include flavor and particle-antiparticle coherence, and they are valid for arbitrary neutrino masses. So the only assumption that we made during the derivation is adiabatic background fields. And in addition to study the collision terms accurately, we also derived some kind of set of generalized Feynman rules, which allows us to compute the collisions for those coherently mixing neutrinos. And this is roughly the idea. And then a somewhat quick outlook of the our formalism. So we started from the contour Swinger Dyson equations, which are like the Euler-Lagrange equations of quantum field theories, since they describe the evolution of the Green's functions. And they can be written alternatively in terms of 4 real-time Kadanoff-Behm equations, which read in weakness space like this. And we don't need to go into the details. The main point here is that The Canal-Behm equations consist of pole equations, which describe essentially the phase-space structures of the correlators, and then the statistical equation, which describes the statistical evolution of the correlators. And these equations, they are still exact to a given approximation for the self-energy function, which means that they contain information, for example, about the flavor and particle-antiparticle coherences. However, as can be, for example, from the red terms, these are like integral differential equations which contain infinite order gradients. So, of course, these are no use like this. You need to somehow reduce the equations to a practical useful form while keeping the information about the coherence effects. And this is indeed a pretty detailed and delicate issue. And here I will give you only like really rough idea how it can be done. So the process can be divided to 3 different steps, and the first step is related to the fact that the pole equation and the statistical equations, they are coupled together. So if you want to get a density matrix equation, you need to somehow find a way to decouple those equations. And namely, it can be done by splitting the statistical functions into a background and a perturbation part. And important here is that the perturbation, they don't need to be small. It is just a convenient way to divide the solutions. And then there is the second question about localization. So the equations are non-local in spacetime coordinates, which can be seen exactly by these red terms here. So one needs to somehow also localize the equations. And this can be done by many different ways. But in neutral physics, one really useful approximation is the assumption of adiabatic background fields, and it holds basically almost in every neutral physics problem. So it is something valid thing to do. And after this, one basically has local and decoupled quantum kinetic equations, but they are not yet still useful for practical use, since the results are not like maybe so easy to understand. So then it is really convenient to use some kind of projective basis, which is constructed of using energy and Hellis to Projektian operators, and this allows to characterize the solutions of the equations by their eigenfrequencies. And after somewhat lots of algebra, and then after the dust settles, we end up with a pretty messy equations like this. And the complexity of the equations and the large number of indices, it's not due to a bad or cumbersome notation, but it actually reflects the generality of these equations, since we have not, for example, assumed the ultra-relativistic limit, and there are those different coherence effects. But the main point here is that when we neglect the I can say a few things about these equations before. So even though it might look complicated, all those terms have clear physical meanings. So on the left-hand side, there is the usual Liouville term or the advection term. Then on the right-hand side, the first term is the usual Hamiltonian commutator term, which describes the leading time oscillation scales. Then there are the generalized forward scattering terms, and then there is, of course, the collision term. And if we neglect the particle-antiparticle coherence effect, we get this kind of equations which reduces the indices a lot. And if we further assume the ultra-relativistic limit, we get just the usual density matrix equations. And I will come back to the implications of these equations a bit later on. But before going there, even though we have now derived formally the quantum kinetic equations, there still remains the question that how one can compute the collision terms. So first of all, we cannot use the usual non-coherent Feynman rules, because then we would neglect the collisions between coherent particle species, which basically means that we would lose the information about the particle-antiparticle coherences. And another thing which is extra here is that we can study the role of flavor coherence in collisions from a bit different point of view than usual. And about the collision terms, using the similar kind of formalism as for the quantum kinetic equations, we were able to show that even in that more general case, the collision term can always be written in this familiar and usual form. So here in the red, there are the usual phase space element, which now contains more indices due to the coherences. Then in the blue, we collected all the distribution functions there. And then in red, there is the invariant matrix element squared. So even while you are considering the coherence effects, the computation of the collision terms reduces essentially that you need to only compute the matrix element squared. And to do that, there we derived the so-called Feynman rules. So again, we don't need to go into the details of these propagators or indices, but the main point here is again that the procedure is exactly as usual in thermal quantum field theory. First you identify the necessary processes, then you draw the corresponding diagrams and the statistical cuts which correspond to the processes that you are interested in, and after that it is just mechanical work. If you want, you can compute them by hand, we have done it, and also if you don't want, just use computer. Mathematical will compute any traces pretty fastly and nicely for you. And after these pretty long derivations, the relevant question is that what is it used for? Why did we bother to do something like that? And even though from the motivation in the beginning it might not be so clear, but by using those methods that we did, we are able to show that the particle-antiparticle coherence actually cancels at any loop order from the collision terms. So you really don't need to worry about that. And the also, they cancel, of course, from the forward scattering terms and from everywhere else in the quantum kinetic equations. So this means that if we assume the ultra-relativistic limit, we reduce the quantum kinetic equations, which were derived by Georgi and Gunther in the early 90s. So our main message is that for neutrinos in almost any problem, you can use just the usual ultra-relativistic quantum kinetic equations, and you don't need to worry about these some maybe more exotic or so maybe unusual quantum coherence effects. However, there are some new implications or uses for our formalism, and they are mostly related to the study of decoherence effects, quantum entanglement, and stuff like that. And the reason why we can say something about this is that during the decoupling and localization process, we divided the problem to pretty many steps, and we kept like exact track of all of the assumptions and like gradient expansions or whatever we did. So due to that reason, we, for example, can say that where the information about the quantum entanglement lies, and we have a pretty good idea how you can take it into account if you wish. Of course, it will be a lot of work because you have to take higher order gradients into account, but it basically allows that. And then due to the flavor dependence of the velocity term, we can, for example, discuss the decoherence effects of like propagation of neutron states. So in a nutshell, if the propagation distance is really long for neutrinos, for example, from supernova to Earth, and the velocity term depends on flavor states, it would in principle mean that am I on overtime? Okay, yeah. So it would in principle mean that different flavor components of the density matrices, they would separate during really long distances. And we have a paper coming about this topic, and I think that Georgi and others have studied this before, but we have like a somewhat different starting point, and so that those coherences could occur, but to our preliminary results, they do not. So there's no decoherence when the neutrons propagate from Earth to, for example, supernova to Earth, based on these velocity terms. And one thing about the Gunther's speech in the morning, he said that there is those questions that can you rotate the Matter-Hamiltonian in the equations and get those some components off. So we actually discussed that question in our paper, and due to our pretty formal approach, we can answer many questions like that. And then this would be a complete new topic for speech, but in the localization decoupling process, it is closely related to how the observer system interference affect to the evolution of the system. And really shortly, you can basically study this by introducing some wave functions, and it is related to the accuracy of the information about the system. And this basically gives you a nice way to do it. So we just demonstrated it shortly, so we don't have like any nice fancy results about this yet, but using our formalism, it is basically possible to do also. And that is basically everything. So to my really short summary, what we did is that we derived a somewhat formal quantum kinetic equations, and our main result is that the old quantum kinetic equations, they are completely fine at the ultra-relativistic limit, and you don't need to care about basically particle-antiparticle or Hellis-2 coherence, even though in this paper we didn't discuss Hellis-2 coherence. We hope that we will publish a paper about that in a couple of months too. But that's it, and I want to thank you for your attention.
Thank you very much. Comments? Or questions?
You mentioned the collisions between flavor off-diagonal terms.
Yes.
Are they like emergent degrees of freedom? What
Now
do
I
you mean
didn't
by
understand.
this?
Are they
Like emergent degrees of freedom? What kind of?
It basically means that your density matrix, it has off-diagonal components, and also those will introduce you, basically, if you consider only flavor diagonal collisions and you neglect the off-diagonal components, then you will essentially get only terms which are proportional to the squares of the ST and U channels. But if you also allow like the off-diagonal components, then you get interference terms of the ST and U channels with like a flavor structure that arises from basically from here. But I think that was in the paper and formalism by Georgi and Gunther already in the 90s.
Okay, I see. Thank you.
Do you have some results of numerical calculations to show us?
No, not numerical, because we were focusing on developing this formalism, and then we reproduced like a bunch of known results. We computed, for example, the collisions in supernova, we computed the active sterile neutrino mixing, we computed neutrino scattering terms, and we wanted to show that basically that the collision terms do work and the forward scattering terms, they are correct. So if that is related to the question that why we did it, is that we wanted to start from like really fundamental level and go like by small steps and like prove every step in the process like exactly that they are okay and that we are not missing anything.
So until now it was analytic work in a way?
Yes.
Okay.
And the next things that we are gonna discuss are related how magnetic fields arise from the swing Dyson equations and how they give the effective magnetic moment to neutrinos and how that affects to the coherence effects. And after that, we are basically studying these decoherence effects. And one main thing about our formalism is that because we kept so close track of all these gradient terms, we don't need to do numerical simulations because we can basically see analytically, for example, the cancellation of the particle-antiparticle coherence. We don't need to basically do numerics because we have the formulas. We can just take and prove it in general for any loop or the computations that they do cancel.
Very nice.
Yes.
I like analytics.
Yes. Yeah, yes, didn't say it, forgot it. Yes.
Yeah, in this context, let me follow up with a question. When you project applications of this formalism for simulation, for calculations, for quantitative analysis, what are the scales you want to consider? Time, space? What is the problem scale you have in mind?
Basically the same as in the Georgis and Gunter's and Wolbe's works, because we found that you don't need to care about those quantum coherence effects, so then the scales are as usual. But if the particle-antiparticle coherence would be important, then the scale would be like extremely small. You would be talking about a femtometer scale or something like that. Then you would have to worry about possible resonances that could occur at femtometer scale, and that would be pretty bad for the numerics and simulations. So now, because you don't need to our understanding and to my understanding, you don't need to worry about those, so the scales are the usual.
Since I have a follow-up question in general, because I followed these days, today in particular also with a lot of theorists presenting their approaches, different concepts, fundamental ones, and I haven't seen a discussion session for tomorrow, which is probably also not the best day. Friday people depart, and then we don't have. Is there a possibility now to discuss, let me say, the bottom line, which one can draw? Where are we? What is the understanding, the level of understanding? Where are the loopholes? I mean, I already see from the previous talk that whenever somebody suggests some practical approach like AI is always fashionable. I mean, you don't need to think, you just put something in a machine and it works. You think so. But we need to train it. And I mean, we need to know that what we use for the training is actually reliable. Otherwise, we will just, again, produce parametric results. We hide parameters in a big machinery. I've seen such developments over decades in astrophysics. The bigger the machine, the more people like the results because we don't know what's in there and we get something out and can use it further. This is not real progress, in my opinion. I mean, parameterizing things in a simple way is the best because you can then see what you have done. So what is now for the practitioners in the field, for the people who want to apply the message? Can we train AI networks with something we have a solid basis on, or is it just busy work, which keeps us entertained for the next decade without really knowing whether we make progress? Is there a possibility to discuss this here, or will we depart tomorrow noon and everyone goes out here and says, I'm completely confused, I don't know where I'm going, or I continue to do what I anyway have done?
But when we are having that discussion, I'm the wrong person to be here, so I will leave the people with more knowledge to speak.
No, but if what we heard in the talk is done, and is done analytically, I mean, this is the basis for training and so on. If it is done analytically with sufficient good precision, and I hope you did it.
We can discuss it afterwards if you wish, because we actually spent really much time to do these processes. Like, we motivated each step pretty well, and to our hope, they are easy to understand, those steps, but I have heard that they might involve some complicated mathematics, but in a way, these are pretty accurate, so we are pretty confident that our derivation is like waterproof, that for light neutrinos and for heavy neutrinos, these do hold.
Have you looked also at the work by the collaborators?
Yes.
They also make a very rigorous derivation of the magnetic equations, including helicity coherence.
Yes, yeah, they did it for helicity coherence, and what is important thing is that they just dropped these red terms away. They say that, okay, we are gonna do some epsilon expansion, and that's like a big difference between our work. So they just said that we are expanding in epsilon, which basically means those gradients, and to my understanding, again, I might be wrong because I'm not so experienced yet, but to my understanding, they study exactly helicity coherence. And because they do the epsilon expansion, they lose the information about the particle-antiparticle coherence, but it also means that because the quantum entanglement and the decoherence effects, they are living in these gradients. So, to my understanding, they lose the information about them. But for helicity coherence, I think their work is good and okay, and I have nothing to complain about it. So.
I just want to tell you my point of view on that. I think the theoretical calculations are pretty clear now. But that doesn't mean there is a simple solution, right? Because if you want to do this in 3D and you have a hierarchy of scales, this is the problem, I think. I think there is no doubt on these equations there. But, you know, in solving in 3D plus 3 momentum directions and 1 time, and you have many different scales, that is the real challenge, in my opinion.
So I completely agree, because if we look at the like usual quantum kinetic equations and the collision terms, you can ignore the number of indices here, but basically you have many dimensions of freedom and you would need to integrate over pretty many dimensions, and if there are, not if, but when there are those fast flavor conversions, you would need to have like really small scale over the whole phase space. So. And to the Gunther's comment, I would like to continue that, yes, I think that again, to my understanding, like the level of the ultra relativistic limit for light neutrinos, the quantum kinetic equations, they should be like good, and at least for my interests, the next questions are to study those decoherence effects and quantum entanglement and those corrections. To our preliminary understanding, or Kimmo's preliminary understanding, who's my supervisor, we think that for most of the cases they are of no importance. But of course, take this with caution. I might be telling lies to you and to myself, but I think they are at least some of those interesting theoretical questions.
My understanding is very limited at this point, but as I understand, you're not losing information about entanglements either. Is that correct?
We are here because the entanglement, it is contained in these gradients, and if you assume adiabatical background field, you can consider these gradients, not those ones k-hats there, but these ones in front mostly to the lowest order. And at that point, you lose the information about quantum entanglement. And if you want to study the quantum entanglement, you have to consider these gradients to higher orders. And the first approximation would be that you take like the first order derivatives. It is complicated sum of derivatives, but like the first order expansion in derivatives into account. And of course, it would give you like pretty many complicated things in the decoupling, localization, and even this, because then you would have to define the basis differently. But that is, to my understanding, again, like the steps how you can study quantum entanglement, like from the perspective of Schwinger-Dyson equations.
Yeah, this is what I was to ask next. What's the relation between this formalism and the Bogoliubov hierarchy that Christina was
I think Christina can
Yes,
answer that question better.
Before losing this information about entanglements, there should be a relation between the two. Maybe not after, but...
But for me the problem is that I don't know so much about the PPQGY approximation, because we wanted to start from like just thermal quantum field theory, and like the Schwinger-Dyson equation, which was derived more than 50 years ago, and which is like the basis for the whole quantum field theory. So we wanted to start it from there, because we don't need to introduce like creator or destroying operators or anything like that. We can only consider like fields and ensembles of particles and use the like fundamental quantum field theoretical approaches. So unfortunately, my understanding isn't enough to comment the differences. Yes. Yeah. Yes, I will have to look at that. Thank you.
Va bene. I don't know if there are more questions. No more questions? Okay, I think we can thank Harry again.